Picture a world where the sun looms 3 times larger in the sky, where days are scorching enough to melt metal and nights plunge into icy darkness so deep it defies imagination. This isn't science fiction, it's Mercury, the solar system's smallest and strangest planet, a place of extremes that scientists still struggle to understand. Despite being our closest planetary neighbor to the Sun, Mercury guards its secrets fiercely, hiding puzzles that defy explanation and challenge everything we thought we knew about how planets work. From its bizarre magnetic fields to the ghostly hollows scattered across its surface, this tiny world is a treasure chest of cosmic mysteries waiting to be unlocked. What makes Mercury so baffling? For starters, it shouldn't even exist. According to early models of the solar system, a planet this close to the Sun would have been ripped apart or swallowed whole by the star's immense gravity. Yet here it is, clinging to its orbit against all odds, wrapped in a magnetic field that behaves like nothing else in our cosmic backyard. Then there's the case of its inexplicable dark patches, regions so oddly reflective that they spark debates about alien materials or hidden reservoirs of ancient, shadowy ice. And let's not forget the planet's baffling density, packed with so much metal that scientists wonder if it's the surviving core of a far larger world, mysteriously stripped bare by some cataclysmic event. That's just the beginning. Today, we're diving deep into 25 of Mercury's most jaw-dropping enigmas, phenomena so strange they've left even the sharpest astrophysicists scratching their heads. Some of these mysteries might hold clues to the birth of our solar system, while others could rewrite the rules of planetary science altogether. So buckle up, because we're about to embark on a journey to the edge of the Sun's furnace, where every crater, cliff, and swirling magnetic anomaly tells a story we're only just beginning to decode. By the time we're done, you'll see this tiny, overlooked world in a whole new light. And trust me, some of these revelations will make your jaw drop, ready to uncover what's really going on out there. Let's go. If you think Mercury's craters are bizarre, just wait until you hear about the hollows, the planet's most haunting geological oddity. Picture this: scattered across the scorched, sun-baked surface are thousands of shallow, glimmering depressions, some no bigger than a house, others stretching for miles. These aren't your average impact craters or volcanic pits. They're eerily bright, almost as if someone dusted them with celestial glitter, and they're found in places where no known geological process should leave such delicate, shimmering scars. Scientists call them hollows, and their existence defies everything we thought we knew about how rocky planets evolve. The mystery deepens when you ask how these hollows formed. One leading theory suggests they're the work of volatile materials, substances like sulfur or even water, ice trapped beneath Mercury's surface for billions of years. When exposed to the brutal heat of the Sun, these materials might not melt but instead skip straight from solid to gas in a process called sublimation, leaving behind these ghostly pits. But here's the catch. Mercury's surface temperatures swing from 800 degrees Fahrenheit during the day to -290 at night. That kind of extreme should obliterate volatile compounds, yet the hollows persist, some even appearing fresh, as if they're actively forming today. Even NASA, a messenger spacecraft which orbited Mercury for 4 years, couldn't crack the case completely. The probe's data revealed that hollows often cluster inside craters or along their rims, hinting at some hidden layer of material lurking just below the surface. Some scientists speculate this could be remnants of Mercury's ancient, volatile, rich crust, while others wonder if meteorite impacts unearthed deeper deposits we've never seen before. And then there's the eerie brightness. These hollows reflect far more sunlight than their surroundings, suggesting their composition is wildly different from the rest of the planet. Could it be some exotic mineral, a previously unknown form of space weathering? The strangest part, hollows aren't just relics of the past. time-lapse images from MESSENGER show some hollows expanding, their edges retreating like shrinking ice caps. That means whatever's carving them is still at work, sculpting Mercury's surface in real time. No other planet in our solar system has features quite like these, making them a one-of-a-kind enigma. Whether they're proof of hidden water, alien minerals, or some entirely new geological process, one thing's clear: Mercury's hollows are rewriting the textbook on planetary science, one glittering mystery at a time. Mercury's magnetic field shouldn't exist, at least not according to everything we know about how planets work. This tiny world, barely larger than Earth's moon, spins so slowly that a single day lasts 59 Earth days. Yet somehow, against all odds, it generates a detectable global magnetic field, a feature usually reserved for larger, faster-spinning planets like Earth or Jupiter. That's like finding a pocket-sized generator powering an entire city. It defies logic, and scientists are still scrambling to explain how Mercury pulls it off. The mystery starts with the dynamo effect, the process that creates planetary magnetic fields. Deep inside Earth, swirling currents of molten iron generate our protective magnetic shield. But Mercury's core should have cooled and solidified billions of years ago, snuffing out any chance of a dynamo. So why is it still active? One theory suggests Mercury's core isn't entirely solid, that a sliver of molten metal somehow persists, churning unpredictably near the planet's outer layers. Others propose that the immense tidal forces from the sun's gravity keep the core partially liquefied, like kneading dough to keep it soft. But here's the twist: Mercury's field isn't just weak, it's lopsided, stronger in the northern hemisphere and oddly offset from the planet's center. Then there's the field's bizarre behavior. During NASA's MESSENGER mission, the spacecraft recorded sudden, erratic spikes in magnetic strength fluctuations so wild they'd be unthinkable on Earth. Some researchers speculate these could be caused by solar wind particles slamming into Mercury's surface, temporarily magnetizing patches of its crust. Others wonder if the planet's core has an uneven composition, with dense metallic clusters creating chaotic currents, the most mind-bending possibility. Mercury's dynamo might operate in pulses, flickering on and off like a cosmic light bulb with a loose connection. What makes this puzzle even stranger is the comparison to Mars. The red planet, nearly twice Mercury's size, lost its magnetic field long ago, leaving its atmosphere to be stripped away by solar radiation. Yet somehow, tiny Mercury, battered by even fiercer solar winds, still clings to its wispy magnetic shield. Could its core contain exotic elements we haven't discovered, or is there some fundamental flaw in our understanding of how magnetic fields form? Every new discovery peels back another layer of mystery, proving that this scorched little world is anything but ordinary. One thing's certain: Mercury's magnetic field isn't just a scientific curiosity, it's a cosmic Rosetta Stone. Deciphering its secrets could reveal how other small, rocky planets across the galaxy generate their own magnetic shields, or why some lose them entirely. For now, though, it remains one of the solar system's most stubborn enigmas, a reminder that even the smallest worlds can hold the biggest surprises. Deep within Mercury's shadowy polar craters lies a substance so dark it absorbs nearly all sunlight, a stark contrast to the planet's otherwise reflective surface. This mysterious material, spotted by NASA's MESSENGER spacecraft huddled in permanently shadowed regions, has sparked a debate that straddles the line between planetary science and cosmic detective work. What makes this stuff so perplexing? For one, it's not just dark, it's inexplicably dark, with a spectral signature that doesn't match any known mineral or compound we've seen elsewhere in the solar system. One leading hypothesis suggests it could be carbon-rich organic material, delivered by comets or asteroids over billions of years. On Earth, similar carbon compounds form the building blocks of life, but on Mercury, they'd be trapped in a frozen, airless purgatory. Here's the catch: Mercury's daytime temperatures are hellish enough to vaporize most organics, Yet these deposits persist in the crater's frigid, sunless recesses, some colder than Pluto. Could they be remnants of ancient impacts preserved like cosmic time capsules? Or does Mercury's surface chemistry somehow alter incoming material into something entirely new? Then there's the volcanic angle. Some researchers argue the dark patches might be remnants of explosive eruptions from Mercury's fiery past. When the planet's interior was still seething, volcanic gases could have deposited layers of graphite or other carbon-based minerals onto the surface. Over eons, meteorite impacts might have shattered and redistributed this material into the poles. But if that's true, why don't we see similar deposits elsewhere? And why does the darkness seem so fresh in places, as if it's being replenished? The plot thickens when you consider alternative explanations. Could solar wind, the relentless stream of charged particles from the sun, be bombarding Mercury's surface and darkening exposed minerals over time? Experiments show that simulated solar wind can blacken certain rocks, but the process shouldn't create patches this stark or localized. Others speculate about exotic forms of space weathering unique to Mercury's extreme environment, where the lack of atmosphere and relentless heat cycles might forge materials we've never encountered. What's truly tantalizing is what these dark stains might reveal about the solar system's history. If they're organics, they could hint at how life's ingredients spread across planets. If they're volcanic, they might rewrite our understanding of Mercury's geologic violence. And if there's something else entirely, well, that's the kind of mystery that keeps scientists awake at night. One thing's certain, until we land a probe in those craters to scrape up a sample, this enigma will keep its secrets locked in the shadows. Just beyond the rim of Mercury's colossal Caloris Basin lies a nightmarish landscape, a twisted, shattered terrain that looks as though the planet's crust was hurled into a cosmic blender. This is the chaotic terrain, a sprawling maze of fractured plateaus, tilted blocks, and jagged valleys stretching hundreds of miles in every direction. It's one of the most violent-looking places in the solar system, yet its origins remain hotly debated. Did it form in the apocalyptic aftermath of the Caloris impact? Or is it the scar of something even more explosive bubbling up from Mercury's depths? The leading theory points to seismic chaos. When the asteroid or comet that carved out Caloris Basin struck Mercury, the force would have been unimaginable, equivalent to detonating 1 trillion nuclear bombs at once. The shockwaves could have rippled through the planet's crust like tsunamis through ice, shattering the landscape on the opposite side of the globe. In fact, there's a region directly antipodal to Caloris called the Weird Terrain, where the ground appears to have been scrambled by these very waves. But here's the problem. Mercury's chaotic terrain isn't just cracked, it's displaced, with massive slabs of crust shifted miles from their original positions. That level of disruption suggests something more than just shaking. Some scientists argue the impact might have triggered volcanic eruptions, liquefying patches of the surface and allowing entire sections to slide like broken puzzle pieces. Then there's the volcanic camp. Mercury's history is littered with evidence of ancient lava flows, and the chaotic terrain sits atop some of the planet's most geologically active ancient regions. Could underground magma chambers have collapsed, causing the surface to slump and fracture? Or did explosive eruptions driven by volatiles like sulfur or water literally blow the crust apart? The puzzling part is the terrain's uneven distribution. Unlike the neat webs of fractures seen on Earth's tectonic plates, Mercury's chaos is concentrated in bizarre, isolated clusters. That patchiness hints at something more erratic, like pockets of volatile materials vaporizing beneath the surface and leaving behind collapsing voids. The wild card, temperature. Mercury's extreme heat cycle, scorching by day, freezing by night, could be slowly tearing the planet apart. Over billions of years, the constant expansion and contraction might have turned the crust brittle, priming it to implode into chaos when the Caloris impact delivered its final blow. Imagine baking a clay pot, then plunging it into ice water. The result would be a network of fractures not unlike what we see here. Yet even this explanation feels incomplete because no other planet in the solar system shows terrain quite like this despite similar temperature swings. What makes this mystery so compelling is the lingering possibility that we're seeing multiple catastrophes frozen in time. The chaotic terrain might be a palimpsest, a layered record of impacts, volcanic tantrums, and planetary stress all woven together. Until we land a rover amid those shattered plateaus to study them up close, this landscape will remain one of Mercury's most haunting riddles. One thing's clear: whatever happened here wasn't just violent. It was planetary surgery without anesthesia, and Mercury's crust never fully recovered. Volatiles are the solar system's delicate wanderers, elements like sulfur, potassium, and even water that vaporize easily under heat. Conventional wisdom says they shouldn't survive on Mercury, where daytime temperatures roast the surface enough to melt lead. Yet here's the shocker: this scorched world is littered with them. Mercury's surface boasts more sulfur than Earth's, and potassium levels defy every model of planetary formation. This isn't just a curiosity, it's a full-blown rebellion against the rules scientists thought governed how rocky planets are born. The puzzle starts with the nebula hypothesis, the long-standing theory that planets form from a swirling disk of dust and gas around a young star. In this model, heat from the newborn sun should have vaporized volatiles near Mercury's orbit, leaving behind only refractory elements, sturdy metals, and silicates that can endure extreme temperatures. That's why, for decades, astronomers assumed Mercury would be bone dry, a barren ball of iron and rock. But when NASA messenger spacecraft started analyzing the planet's composition, the data delivered a knockout punch. Mercury's crust is surprisingly rich in sulfur, with some regions containing up to 4% by weight. For comparison, Earth's crust averages just 0.06% sulfur. Potassium, another volatile, is also overrepresented, appearing in ratios to thorium that mirror Mars, a planet 5 times farther from the Sun. So how did these fragile elements escape annihilation? One radical theory suggests Mercury might not have formed where it orbits today. Instead, it could have originated farther out in the solar system, where volatiles were more abundant before being hurled inward by gravitational chaos. Imagine a snowball surviving a trip through a bonfire somehow. Mercury's volatiles endured the journey. Other researchers propose that Mercury's building blocks were coated in a protective layer of graphite, shielding sulfur and potassium from the sun's wrath during the planet's infancy. There's even a wilder idea that Mercury's volatiles were delivered later, bombarded onto its surface by countless comets and carbon-rich asteroids over billions of years. But the plot thickens when you consider Mercury's volcanic past. The planet's vast plains are ancient lava flows, and sulfur's presence suggests it was dissolved in that molten rock. If Mercury's mantle was once rich in sulfides, volcanic eruptions could have spewed them onto the surface, creating a sulfurous crust that persisted despite the heat. Yet this raises another question: why didn't the sun's radiation strip these volatiles away over time? The answer might lie in Mercury's lack of atmosphere. Without wind or weather to erode the surface, sulfur compounds could remain locked in the rock, undisturbed for eons. The implications are staggering. If Mercury can cling to volatiles against all odds, it forces us to reconsider how planets accrete materials, and where Earth's own water and organics might have come from. Even more tantalizing, this tiny world might hold clues to the hidden reservoirs of volatiles lurking in other star systems. For now, though, Mercury's overabundance of sulfur and potassium remains a cosmic contradiction, a reminder that the universe loves to defy our neatest theories. Every time we think we've figured out the rules, a planet like this whispers, "Think again." On Mercury's sun-scorched face, there's a structure so bizarre it looks like something out of a sci-fi nightmare: the Pantheon Fossae, a sprawling network of troughs radiating from a central point like cracks in a shattered windshield. But the most jaw-dropping feature, the spider, a cluster of over 100 narrow grooves fanning outward in perfect symmetry, some stretching over 20 miles long. This isn't just another crater or lava flow. It's a geological anomaly so unique that scientists still can't agree on how it formed, even after years of scrutiny from orbit. One school of thought points to volcanic forces. Imagine a blister forming on Mercury's crust as magma pushed upward, stretching the surface until it fractured like overstretched taffy. The spider's radial pattern could be the result of such an uplift, with the troughs marking the spots where the crust finally gave way under pressure. Supporting this, messenger spacecraft data revealed that Pantheon Fossae sits within Caloris Basin, a colossal impact crater packed with volcanic plains. If magma welled up beneath this region, it might have created a dome that later collapsed, leaving behind these eerie, spoke-like scars. But here's the catch. Most volcanic uplifts on other planets create circular or oval fractures, not this precise radial symmetry. The spider's near-perfect geometry suggests something far more peculiar at work. Then there's the impact hypothesis. Some researchers argue the spider's center might mark the bullseye of a secondary impact, a smaller asteroid striking Mercury long after Caloris formed. The energy from such a hit could have sent shockwaves rippling outward, fracturing the brittle crust in this starburst pattern. Yet even this explanation feels incomplete. Impact craters typically leave behind raised rims and ejector blankets, none of which appear here. Plus, the troughs are too uniform, too delicate for the chaos usually wrought by a cosmic collision. The wildcard, tectonic weirdness. Mercury's crust is under constant stress from the planet's slow cooling and contraction, causing it to shrivel like a raisin over billions of years. Could the spider be a freak result of this global squeeze, with the radial cracks forming as the crust buckled in just the right or wrong way? It's a compelling idea, except no other contraction features on Mercury or any planet look remotely like this. What makes the spider truly mind-bending is its isolation. Nothing else in the solar system matches its eerie precision. Is it a volcanic fluke, a ghostly impact relic, or evidence of some entirely unknown geological process? Until we sink a probe's drills into those troughs, this enigmatic structure will keep spinning its web of mysteries, reminding us that even in a universe full of wonders, Mercury still has tricks up its sleeve. Mercury isn't just cooling off, it's shrinking, crumpling in on itself like a grape left too long in the sun. Across its sun-blasted surface, massive cliffs slice through the landscape, some towering over a mile high and stretching for hundreds of miles. These aren't your typical mountain ranges or erosion scars, they're tectonic wrinkles, evidence of a planet that's been slowly tightening its belt for billions of years. And the strangest part, this cosmic contraction might still be happening today, reshaping Mercury in real time right under our noses. These gargantuan scarps, called lobate scarps, are the smoking guns of planetary shrinkage. Picture a dried-out riverbed, its mud cracked and curled as the water evaporated. Now imagine that on a planetary scale, with Mercury's entire crust fracturing as its molten core cools and solidifies. The math is staggering. Since the planet's formation 4.5 billion years ago, its radius may have contracted by as much as 9 miles, enough to buckle the surface into these dramatic, blade-like ridges. But here's where the mystery deepens. Unlike Earth, where tectonic plates jostle and slide, Mercury's crust is a single, unbroken shell. When it contracts, there's nowhere for the stress to go but up, forcing sections of the surface to thrust violently over one another in a process that's more like a planetary-scale avalanche than anything we see on our own world. What's truly baffling is how young some of these scarps appear. High-resolution images from the MESSENGER probe reveal scarps cutting straight through impact craters, craters that themselves are relatively fresh, geologically speaking. That means the shrinkage isn't just some ancient relic. It's likely an ongoing process, with Mercury's crust still creaking and groaning as it adjusts to the cooling inferno below. Some scientists even speculate that the planet could still experience Mercury quakes, seismic ripples shaking the surface as new scarps form. The comparisons to other rocky worlds only make this phenomenon weirder. Mars, for instance, shows signs of early contraction, but its scarps are smaller and more subdued, hinting that its cooling process stalled long ago. Earth, with its churning mantle and plate tectonics, doesn't shrink at all. It recycles its crust. Mercury, though, it's in a league of its own, contracting more dramatically than any other planet in the solar system. Why the disparity? One theory points to Mercury's unusually large iron core, which makes up a staggering 85% of the planet's radius. As that core cools, it's not just shrinking, it's crystallizing, with solidifying iron releasing enough latent heat to potentially drive volcanic activity, even as the planet overall deflates. Then there's the wild card, the Sun's relentless gravitational tug. Mercury's oblong orbit subjects it to extreme tidal forces, which might be kneading the planet's interior like putty, keeping it just warm enough to continue contracting at a snail's pace. Combine that with the daily temperature swings enough to make the surface expand and contract like a breathing organism, and you've got a recipe for geologic chaos. The implications stretch far beyond Mercury. If this tiny world is still actively shrinking, it challenges our assumptions about how rocky planets age. Should we expect the same from exoplanets orbiting close to their stars? And what does it mean for Mercury's future? Will it one day crumple into a planetary raisin, its surface a labyrinth of overlapping scarps? For now, the answers remain locked beneath those cliffs, silent witnesses to a slow-motion collapse that's been billions of years in the making. Every new image from orbit peels back another layer of the mystery, proving that even a planet's death grip can be as fascinating as its birth. Beneath Mercury's vast volcanic plains, the ghosts of a violent past linger, pale, circular outlines barely visible beneath layers of hardened lava. These are the so-called ghost craters, the spectral remains of ancient impacts that were nearly wiped off the planet's face by catastrophic eruptions. Unlike any other world in the solar system, Mercury boasts dozens of these eerie formations, their rims softened and buried but not quite erased, like footprints frozen in concrete. They're more than just geologic curiosities. They're time capsules preserving clues to a period when the planet was a cauldron of fire and fury. What makes these ghost craters so puzzling? For starters, they shouldn't be here at all. When lava floods an impact crater on most planets, it usually fills and obliterates it completely, leaving little trace of the original structure. But Mercury's lava flows behaved differently. Instead of swallowing craters whole, they partially submerge them, leaving behind faint, circular outlines that look almost like submerged dinner plates. One theory suggests this odd preservation is due to Mercury's low gravity, just 38% of Earth's. With less gravitational pull, lava might have spread more thinly, flowing around crater rims rather than overwhelming them. Another idea points to the lava's viscosity. If Mercury's molten rock was unusually runny, it could have seeped into craters without fully erasing their edges. The real surprise, these ghosts aren't just relics, they're active storytellers. By studying their sizes and distributions, scientists have pieced together a timeline of Mercury's volcanic heyday. The largest ghost craters, some spanning over 60 miles wide, must have formed during an era of apocalyptic eruptions when lava oceans drowned entire regions of the planet. Smaller ghosts, meanwhile, hint at later, more localized floods. Together, they paint a picture of a world that didn't just erupt once, but in waves, with each pulse of volcanism leaving its own layer of evidence. But the mystery deepens when you ask why Mercury's volcanic activity was so extreme. Earth's volcanoes are fueled by tectonic plates shifting and grinding, but Mercury has no such plates. Instead, its eruptions might have been driven by the planet's shrinking core, which could have squeezed magma to the surface like toothpaste from a tube. Or perhaps giant impacts like the one that created Caloris Basin, triggered volcanic outbursts by fracturing the crust and releasing pent-up magma. Some ghost craters even overlap, revealing where later lava flows partially buried older ones, a geologic palimpsest that suggests Mercury's firestorms weren't just violent but episodic. The most haunting detail, these craters might still be shaping Mercury today. Some ghost craters show signs of hollows, those bright, mysterious depressions that suggest volatile materials are escaping from beneath the surface. If so, these ancient scars aren't just silent, they're breathing, exhaling whispers of gas and dust into the vacuum. That means Mercury's ghost craters aren't merely fossils, they're active participants in the planet's slow-motion transformation. Every faint outline, every half-buried rim, is a testament to a world that refuses to sit still, even in death. What's clear is that these ghostly imprints hold the key to Mercury's most explosive secrets. They bridge the gap between the planet's violent birth and its strange present, offering a rare glimpse into how worlds evolve when caught between fire and ice. And until we land a probe on those lava-soaked plains to study them up close, they'll remain one of the solar system's most enigmatic echoes, faint but impossible to ignore. If there's one thing that shouldn't exist on Mercury, it's ice. This is a world where daytime temperatures hit 800 degrees Fahrenheit, hot enough to melt zinc, and where the sun blazes 3 times larger in the sky than it does from Earth. Yet somehow, hidden in the pitch-black depths of the planet's polar craters, NASA messenger spacecraft found something impossible: vast deposits of water ice, some as thick as 50 feet. These frozen reservoirs lurk in perpetual shadow, shielded from the sun's fury by crater walls that never see daylight. But the real shocker, there's so much ice that if you spread it across Washington, D.C., it would blanket the city in a layer 2.5 miles deep. The question isn't just how ice survives here, it's how it got here in the first place. Mercury's surface is drier than bone, with no atmosphere to speak of and solar radiation that should have vaporized any trace of water billions of years ago. One leading theory points to comets, those cosmic snowballs that barrel through the solar system. When they collide with Mercury, their ice could get trapped in polar craters, where temperatures plunge to -370 degrees Fahrenheit colder than Pluto. Over eons, these impacts might have built up layers of frost, preserved like food in a planetary freezer. But here's the hiccup: Mercury's ice isn't pure. Radar scans reveal patches of dark, organic-rich material mixed in, almost like a layer of cosmic dirt covering the frost, that suggests something more complex than just comet deliveries. Another possibility: the ice might be homegrown. Yes, you heard that right. Even on Mercury, hydrogen from the solar wind could react with oxygen in surface minerals, creating tiny amounts of water molecules that eventually migrate to the poles. It's a slow process. Think centuries, not years, but given enough time, it could explain why the ice seems fresher than expected. Some scientists even speculate that Mercury's volcanic past might have released water vapor from deep underground, which then froze out at the poles. Imagine a planet sweating ice as it cooled. The wildest twist: Mercury's ice might not be alone. Some craters show signs of other volatiles, like frozen carbon dioxide or even methane, huddled alongside the water. These compounds shouldn't last long under Mercury's conditions, yet there they are, defying the odds. Could microbial life, or at least its chemical precursors, be lurking in these icy vaults? Probably not, but the mere existence of organics raises tantalizing questions about how life's ingredients spread through the solar system. What makes this mystery so thrilling is the sheer improbability of it all. Mercury's ice is a cosmic contradiction, a glimmer of frost in a world of fire. It's proof that even the harshest environments can harbor surprises, and that the universe has a way of preserving its secrets in the unlikeliest places. Whether delivered by comets, cooked up by chemistry, or vented from the planet's depths, this ice is rewriting the rules of where water can exist, and who knows, If Mercury can hold onto ice against all odds, maybe other scorched worlds around distant stars are doing the same. For now, though, these frozen pockets remain one of the solar system's most delicious enigmas, a reminder that sometimes the universe saves its coldest secrets for the hottest places. Mercury's exosphere shouldn't exist, at least, not in the form we've found it. Unlike Earth's thick, protective atmosphere, this wispy shroud of gas is so thin that atoms in it collide less often than they escape into space. Picture a cosmic game of tag where the players are so spread out they barely notice each other. Yet despite its ghostly nature, Mercury's exosphere is teeming with surprises. Sodium, calcium, and even magnesium atoms dancing in ways that defy every expectation, caught in a bizarre tug of war with the sun's relentless solar wind. What makes this exosphere so strange? For starters, these elements shouldn't stick around. Sodium, one of the exosphere's standout ingredients, is notoriously flighty, like trying to hold onto glitter in a hurricane. When blasted by solar radiation, it should vanish into space almost instantly. Yet Mercury's exosphere clings to it with sodium concentrations that pulse and shift like a living thing. Some regions flare up suddenly, creating bright patches visible from Earth, while others fade mysteriously. The leading theory, Mercury's surface is constantly replenishing the exosphere, with solar wind and micrometeorites knocking atoms loose in a process called sputtering. But here's the kicker: the sodium isn't distributed evenly. It clusters near the poles and surges on the planet's dawn side, as if guided by some unseen force. Then there's calcium, the exosphere's quiet rebel. Unlike sodium, which glows brightly under sunlight, calcium lingers in the shadows, stubbornly resisting the solar wind's pull. It's heavier, more reluctant to move, yet somehow it reaches higher altitudes than expected, like smoke rising against a stiff breeze. Scientists suspect magnetic fields might be funneling these atoms upward, but Mercury's lopsided magnetism can't fully explain the pattern. Even weirder, calcium levels spike after the planet passes through dense regions of the solar wind, as if the exosphere is somehow feeding off the chaos. Magnesium adds another layer of intrigue. Found in smaller amounts but behaving just as unpredictably, it seems tied to Mercury's surface composition, particularly its volcanic plains. Some researchers think magnesium gets liberated when solar wind particles slam into mineral deposits, while others argue it's volcanic gas that never fully escaped the planet's gravitational grip. The truth might lie somewhere in between, with temperature swings cracking the surface like a dried lake bed, releasing trapped atoms bit by bit, the real head-scratcher. How all these elements interact, solar wind should blast them away, yet they persist in a delicate balance, as if Mercury's exosphere has its own set of rules. Earth's atmosphere is a well-mixed soup, but Mercury's is more like a layered cocktail, each ingredient floating at its own altitude, defying gravity and logic. Some atoms get ionized and whipped into space, while others circle back to the surface, only to be kicked up again. It's a perpetual cycle of escape and renewal, with the sun playing both villain and accomplice. This isn't just academic curiosity. Understanding Mercury's exosphere could reveal how airless worlds across the galaxy lose or cling to their tenuous atmospheres. It might even hint at how volatiles get trapped in shadowed craters, or why some planets end up barren while others hold onto traces of their past. For now, though, this ever-changing veil of atoms remains one of the solar system's most elegant puzzles, a reminder that even the thinnest atmospheres can hold the thickest mysteries. Among Mercury's countless craters, a handful stand out with an eerie, otherworldly glow halos of spectral blue that shouldn't exist on a planet painted in muted grays and browns. These blue halo craters, first spotted in detailed color, enhanced images from NASA, a messenger mission, aren't just visual oddities. They're windows into a subsurface world of exotic minerals, hinting at materials so unusual they've sparked debates about Mercury's hidden chemistry. What makes these halos so baffling? For one, their color is a cosmic red flag. In planetary science, blue tints often signal freshly exposed material. Think of Earth's glaciers, where pristine ice scatters light in similar ways. But Mercury's surface is ancient, bombarded by radiation for billions of years. Anything exposed should have long since weathered to a dull monotone. Yet these halos cling to their brilliance as if something beneath the surface is constantly renewing them. One leading theory points to graphite, yes, the same stuff in your pencil. Early in Mercury's history, its magma ocean may have crystallized layers of carbon-rich minerals which later got churned up by impacts. When asteroids punched through the surface, they could excavate this buried graphite, scattering dark blue-gray particles around the crater rims. Supporting this, messenger spectrometers detected carbon signatures near some blue halos. But here's the wrinkle: graphite should darken over time under solar radiation, yet these halos remain strikingly vivid. That suggests an ongoing process, like micrometeorites constantly sandblasting the surface to reveal fresh material, or even subsurface volatiles escaping through fractures and leaving behind bright deposits. Then there's the volcanic angle. Some blue halos overlap with Mercury's ancient lava flows, hinting they might be stained by minerals like ilmenite or titanium-rich pyroxenes, materials known to reflect bluish light when found on the Moon. If Mercury's volcanic eruptions carried these minerals to the surface, impacts could have scattered them in concentrated rings. But why only around certain craters? And why do some halos appear inside crater walls, as if splashed there by some underground geyser? The distribution defies simple explanations, pointing to pockets of unique chemistry locked beneath Mercury's crust. The wildest possibility: these halos might be linked to Mercury's hollows, those shimmering, enigmatic depressions that pockmark the planet. Both features share a puzzling freshness, as if some active process is uncovering or altering materials in real time. Could the same volatile substances carving out hollows also be responsible for the blue halos, leaching through fractures and staining the surface in surreal hues? It's a tantalizing connection, but one that raises more questions than answers. After all, no other planet in the solar system shows this precise combination of color and geology. What's clear is that these cerulean rings are more than just pretty anomalies. They're clues to Mercury's subterranean diversity, evidence that beneath its scorched facade lies a layered, dynamic world we've barely begun to understand. Whether they're scribbles of primordial carbon, volcanic graffiti, or signs of some unseen upheaval, one thing's certain: Mercury's blue halos are a silent challenge to our assumptions, reminding us that even the most familiar landscapes can hide strokes of the unexpected. Mercury should be drowning in iron, with a core making up nearly 85% of its radius, far bigger than Earth's. You'd expect its surface to be a rusty wasteland, littered with metallic deposits. But here's the cosmic curveball: Mercury's outer layer is starving for iron, showing barely a trace of the metal that dominates its interior. This isn't just odd, it's a violation of planetary logic, a riddle that's forced scientists to rethink how rocky worlds are built from the ground up. One theory throws us back to Mercury's violent infancy. Imagine the young solar system, a chaotic shooting gallery where planets were still taking shape. During this period, a colossal impact might have ripped away much of Mercury's original crust and mantle, leaving behind a stripped-down core with just a thin shell of residual material. Think of it like smacking a watermelon with a sledgehammer. The juicy interior survives, but the outer rind is obliterated. If a protoplanet the size of Mars sideswiped Mercury, the collision could have vaporized its iron-rich surface layers, leaving the planet's core exposed like a cosmic jack-o'-lantern. Later volcanic activity might have then resurfaced the planet with lava poor in iron, creating the paradox we see today. But here's where things get thorny. If Mercury lost so much material, where did it go? Some models suggest the ejected debris could have spiraled into the Sun or been flung out of the inner solar system entirely. Others propose a wilder idea that the missing crust wasn't destroyed, it was stolen. Mercury's orbit brings it perilously close to the Sun's gravitational grip, and over eons, solar tides might have siphoned away its outer layers, leaving behind a metallic husk. Yet even this explanation feels shaky because no other planet, not even scorched Venus, shows such extreme stripping. Then there's the differentiation dilemma. On Earth, heavier elements like iron sank to the core during the planet's molten phase, while lighter minerals rose to form the crust. But Mercury's iron deficiency suggests something far more extreme. Perhaps its entire surface was once molten, with iron so thoroughly drained into the core that only a whisper remained in the outer layers. Supporting this, messenger spectrometers found Mercury's surface rich in magnesium and sulfur elements that typically rise when iron sinks. It's as if the planet went through a geologic centrifuge, separating its materials with unnatural precision. The plot thickens when you compare Mercury to other rocky worlds. The Moon, for instance, has an iron-poor crust too, but that's because its surface is packed with lightweight anorthosite, a mineral that floated atop its ancient magma ocean. Mercury's crust, though, lacks that signature mineral. Instead, it's peppered with volcanic plains and mysterious dark patches, none of which explain the missing iron. Even Mars, with its puny core, shows more surface iron than Mercury. Why is this tiny planet so stubbornly stingy with a metal that should be everywhere? The most tantalizing clue might lie in Mercury's magnetic field. Active dynamos usually require a liquid outer core, and for Mercury's to still churn after billions of years, its core must contain lighter elements like sulfur or silicon, mixed with the iron to keep it from fully solidifying. If these impurities altered how iron was distributed during the planet's formation, they could have left the surface bizarrely depleted. It's a delicate balancing act. Just enough iron vanished to leave the crust barren, but not so much that the core lost its magnetic mojo. Whether carved away by impacts, siphoned by the sun, or locked in a cryptic dance with sulfur, Mercury's missing surface iron remains one of planetary science's most stubborn puzzles. Every probe sent their peels back another layer, but the truth still feels just out of reach. One thing's certain, this planet's secrets aren't just skin deep. They're buried in the very metal that makes it tick, or rather, the metal that isn't there. Mercury's poles are home to one of the solar system's most elusive light shows. Sudden, flickering bursts of X-ray auroras that appear without warning and vanish just as quickly. Unlike Earth's shimmering northern lights, these auroras don't dance in visible hues. They scream in high-energy X-rays, invisible to the naked eye but blazingly bright to spacecraft sensors. And the strangest part, they're not tied to Mercury's magnetic poles like auroras elsewhere. They flare up in random patches, defying every rule we thought governed these cosmic spectacles. The mystery starts with their origin. On Earth, auroras unfold when charged particles from the solar wind spiral down magnetic field lines, colliding with atmospheric gases to create glowing curtains of light. But Mercury barely has an atmosphere, and its magnetic field is a patchwork of weak, lopsided zones. So how does it manage to produce X-ray flares at all? One clue lies in the planet's surface. When solar wind particles, especially heavy ions like oxygen and sodium, slam into Mercury's sun-baked crust at millions of miles per hour, they can kick X-rays out of the soil like sparks from a grindstone. It's a process called X-ray fluorescence, where incoming particles excite atoms in the ground, forcing them to release energy as X-rays. But here's the twist: these auroras aren't steady. They burst to life in sudden, unpredictable flashes, sometimes lasting mere minutes before fading into the void. Timing plays a crucial role. These X-ray flares seem to coincide with solar storms, explosive eruptions from the sun that hurl extra waves of charged particles into space. When these storms hit Mercury's magnetosphere, they might compress it like a soda can, funneling particles toward the surface with enough force to trigger intense X-ray emission. Yet not every solar storm produces a flare, and some auroras ignite during relatively calm solar conditions. That suggests Mercury's crust holds pockets of minerals unusually prone to lighting up under bombardment, almost like cosmic touch paper waiting for a spark. The real enigma, their sheer rarity. Despite orbiting Mercury for years, NASA messenger spacecraft caught only a handful of these events. That implies the perfect storm of conditions, specific solar wind speeds, magnetic field alignments, and surface compositions must converge to create them. It's like trying to predict lightning in a desert. You know the ingredients, but the recipe remains maddeningly opaque. And without a thick atmosphere to scatter the X-rays into broader displays, these auroras remain razor-sharp pinpricks, here 1 second and gone the next. What makes this phenomenon so thrilling is its uniqueness. No other planet, not even Mars with its patchy magnetism, produces X-ray auroras quite like Mercury's. They're a reminder that even the smallest, most airless worlds can host cosmic fireworks if only we know how to look. Whether they're teaching us about solar wind dynamics, exotic surface chemistry, or the chaotic interplay between stars and their planets, one thing's clear: Mercury's X-ray auroras are more than just fleeting light shows. They're flashes of brilliance in the dark, illuminating secrets we're only beginning to grasp. Mercury's poles should be the coldest places on the planet, locked in perpetual shadow, untouched by the sun's blistering rays for billions of years. Yet something bizarre is happening beneath that frozen wasteland. Measurements from orbiting spacecraft reveal patches of warmth where there should only be deep chill, subtle thermal anomalies that scientists have dubbed the hot poles. These regions aren't just defying expectations, they're rewriting our understanding of how heat moves through airless worlds. The enigma starts with basic physics. Without an atmosphere to distribute heat, Mercury's surface temperatures swing wildly between scorching days and frigid nights. But in the permanent shadows of polar craters, where temperatures plunge to -370 degrees Fahrenheit, any warmth should come as a shock. Early models predicted these regions would be icy, inert, and uniformly cold. Instead, infrared scans show faint but unmistakable thermal variations, some crater floors radiating slightly more heat than their surroundings, as if whispering secrets from below. One compelling theory points to Mercury's shrinking core. As the planet contracts, the resulting tectonic stress might generate tiny amounts of internal heat, seeping upward through fractures in the crust like geothermal whispers. On Earth, this process drives hot springs and volcanoes, but on Mercury, even a faint trickle of warmth could nudge polar temperatures a few degrees higher than expected. The catch: this heat would need pathways to reach the surface, and no one's sure how it could traverse miles of rock to warm specific patches rather than spreading evenly. Another possibility involves Mercury's chaotic terrain. The same lobate scarps that crisscross the planet could act as thermal conductors, funneling heat from the interior along fault lines straight to the poles. Imagine cracks in a sidewalk radiating warmth on a winter morning, except these fractures are planetary in scale, potentially channeling energy over hundreds of miles. Some researchers suggest these pathways might even explain why certain craters host ice while their neighbors stay dry. Heat seeping up could create localized melt zones, altering volatile deposits in ways we're only beginning to map. Then there's the wild card: residual volcanism. Most of Mercury's volcanic activity died out billions of years ago, but what if some smoldering embers still linger? Even a wisp of magma trapped deep underground could warm the crust above it, creating subtle hotspots. It's a long shot. No active volcanoes have been spotted, yet the planet's massive core cools slower than expected, leaving room for surprises. Thermal vents, radioactive decay in concentrated mineral deposits, or even ancient lava tubes retaining heat could all play a role in these puzzling temperature spikes. The most tantalizing clue: the warmth isn't random. It clusters near regions where MESSENGER detected hydrogen, a possible sign of water ice. Could the two phenomena be linked? One provocative idea suggests that as volatiles sublimate from ice deposits, they release tiny bursts of heat, creating a feedback loop where escaping gases slightly warm the surrounding terrain. Alternatively, dark material mixed with the ice might absorb just enough stray sunlight to tip the thermal scales. Whatever the cause, Mercury's hot poles are a reminder that even the coldest corners of the solar system can hide unexpected fire. These faint thermal fingerprints might seem minor, but they carry major implications for understanding how planets lose their heat, how volatiles survive in hostile environments, and where to hunt for similar anomalies on worlds beyond our own. Until we land a probe in those shadowed craters to take their temperature firsthand, this mystery will keep us guessing, proving once again that Mercury's secrets refuse to freeze over. Mercury has a tail, not of fire or ice, but of shimmering potassium atoms stretching thousands of miles into space, flickering in and out of existence like a cosmic mirage. Unlike the static tails of comets or the steady glow of planetary auroras, this one is mercurial in every sense. It balloons to dramatic lengths, then withers to near invisibility, sometimes within days. Earth-based telescopes first spotted this elusive feature decades ago, but even now, its wild fluctuations defy easy explanation, turning what should be a predictable stream of particles into one of the solar system's most erratic spectacles. So why potassium? The element isn't rare, but it's fragile, easily knocked loose from Mercury's surface by the relentless barrage of solar wind and micrometeorites. Once freed, these atoms get swept up by sunlight's gentle push, forming a faint, comet-like tail that streams away from the sun. But here's where the mystery takes hold. On some observations, the tail shines brilliantly, stretching over 1.5 million miles, long enough to reach from Mercury to Earth 6 times over. Other times, it's barely detectable, as if someone turned off a faucet. No other planet's exospheric tail behaves with such volatility, and scientists are racing to figure out what's pulling the strings. Solar activity seems to play a role. During periods of intense solar storms, the tail often flares to its most luminous, as if the sun's fury is shaking potassium loose like dust from a rug. Yet not every solar storm triggers the same response, and sometimes the tail brightens during quiet intervals too. This suggests Mercury's surface chemistry is part of the puzzle. Perhaps certain regions are richer in potassium, releasing it in bursts when heated or struck. There's even evidence that the planet's magnetic field, though weak, might funnel solar wind particles to specific areas, creating localized geysers of atoms that surge unpredictably. Then there's the wild card, Mercury's orbit. The planet's path around the Sun is the most elliptical of any in the solar system, meaning its distance from the Sun varies wildly. At its closest approach, solar radiation is over twice as intense as at its farthest point. Could this extreme swing in sunlight be cooking potassium off the surface in cycles, like seasons of atomic harvest? It's a compelling idea, except the tail's brightness doesn't always sync neatly with orbital position, leaving scientists to wonder if other forces like meteor showers or buried volatiles are also at play. What makes this tail truly bizarre is its asymmetry. Unlike a comet's tail, which fans out evenly, Mercury's potassium tail often skews to one side, as if pushed by an unseen current. Some researchers suspect the solar wind's magnetic fields might be sculpting it, while others point to Mercury's lopsided magnetosphere as a possible culprit. Either way, the tail's shape shifts as unpredictably as its brightness, turning it into a moving target for observers. The stakes for solving this mystery are higher than they seem. Potassium tails aren't just a Mercury quirk, they could be a universal feature of rocky planets bombarded by starlight, offering clues about how atmospheres form and vanish across the galaxy. Every flicker of this elusive tail holds a lesson, a whisper about the delicate dance between planets and their stars. Until we catch it in the act often enough to decode its rhythms, though it remains a celestial strobe light flashing its secrets, then vanishing before we can fully grasp them. Amid Mercury's vast stretches of dull, sun-baked terrain, some craters shine like beacons, patches of dazzling brightness that stand out against the planet's otherwise muted palette. These aren't just slightly reflective, they're unnaturally bright, with albedo levels that rival fresh snow on Earth. In a place where cosmic weathering should have long since dimmed every surface, these gleaming anomalies defy time, sparking debates over what could possibly make them glow so fiercely under the sun's relentless gaze. One leading theory points to the violence of recent impacts. When asteroids or comets slam into Mercury, they blast away the planet's aged, darkened outer layer, exposing fresh material untouched by solar radiation. On the Moon, similar raid craters showcase bright ejecta, but they fade over millions of years as micrometeorites and solar wind dull their shine. Mercury's gleaming craters, however, don't follow that script. Some appear suspiciously pristine, as if their brilliance has resisted the eroding effects of space for far longer than physics allows. That raises a tantalizing question. Could Mercury's surface be hiding minerals that resist darkening, or is some active process continually renewing these radiant patches? Then there's the exotic mineral angle. Spectroscopic data from NASA, a messenger mission, revealed that some bright craters contain unusual concentrations of reflective compounds like pyrozine or spinel, materials known for their ability to scatter light with exceptional efficiency. These minerals might have originated deep within Mercury's mantle, excavated by violent impacts and scattered across the surface like glitter. But here's the wrinkle: not all bright craters share the same spectral fingerprint. Some glow with a bluish tint, while others reflect uniformly across all wavelengths, suggesting multiple mechanisms at play. Could different craters be bright for different reasons, some from fresh impacts, others from volatile outgassing, and still others from subterranean mineral oddities? The plot thickens when you consider Mercury's hollows, those enigmatic, shimmering depressions often found near crater floors. Many bright craters overlap with hollows, hinting at a possible connection. If volatiles beneath the surface are sublimating, they might leave behind bright residues like salt crusts on a dried lake bed. Alternatively, the energy from impacts could trigger chemical reactions in Mercury's crust, transforming darkened minerals into reflective ones. Imagine a cosmic alchemist striking the planet's surface, turning leaden soil into mirrors with every blow. The most perplexing clue: some of these craters aren't just bright, they're getting brighter. Time-lapse images suggest their reflectivity fluctuates, as if something beneath the surface is actively refreshing their shine. That's unheard of on other airless bodies, where craters only darken with age. Whether it's microscopic landslides revealing fresh material or some form of space weathering working in reverse, Mercury's gleaming craters refuse to play by the rules. What makes this mystery so compelling is its defiance of simple explanations. These aren't just static features, they're dynamic, evolving puzzles that challenge our understanding of how planetary surfaces age. Whether they're windows into Mercury's hidden chemistry, monuments to its violent past, or signs of processes we've yet to discover, one thing's clear: in a universe where darkness usually wins, these craters are determined to shine. And until we land a rover beside them to scratch beneath their glittering surfaces, their secrets will remain as bright and as elusive as the sunlight they reflect. Scattered around Mercury's ancient volcanoes lies a landscape that looks like it's been peppered with cosmic shotgun blasts, fields of small, steep-sided pits clustering near vents and fissures like scars from some long-forgotten eruption. Scientists call this the pitted terrain, and it's unlike anything seen near volcanoes on Earth or anywhere else in the solar system. These aren't your typical lava tubes or collapse features. They're chaotic, uneven depressions, some no larger than a car, others spanning hundreds of feet, all packed together in dizzying concentrations. The closer you look, the stranger they get. Their edges are razor-sharp, their floors mysteriously flat, and they seem to avoid overlapping, as if each pit staked out its own exclusive patch of real estate. So what could possibly carve such precise, yet anarchic, scars into Mercury's surface? The prime suspect, explosive degassing. Think of a soda bottle shaken and uncapped, but on a planetary scale. When Mercury's volcanoes were active billions of years ago, they might not have oozed lava as gently as Hawaii's shield volcanoes. Instead, they could have erupted like champagne corks popping, with trapped gases like sulfur, carbon dioxide, or even water vapor bursting through the surface in violent jets. As these gases escaped, they might have left behind collapsed pockets where the ground literally exhaled itself into space. Supporting this, many pits cluster around volcanic vents like bees around a hive, and their shapes match what you'd expect from explosive blasts: steep walls, flat floors, and no debris piles. But here's the catch: degassing alone doesn't explain why these pits are so selective in their distribution. Why do some volcanic plains have them, while others, just as ancient, remain pit-free? Then there's the volatile angle. Mercury's crust might hide unstable compounds like chlorides or sulfides just beneath the surface. When magma heated these materials, they could have vaporized instantly, triggering underground explosions that left behind these pockmarks. Imagine lighting a firework buried in sand. The result would be a pit blasted clean, with no loose material left behind. This might explain why some pits appear inside lava flows, as if the ground caved in long after the eruptions ended. Even weirder, a few pits seem to have formed recently, at least in geological terms, suggesting Mercury's subsurface might still hold pockets of volatiles ready to blow. But the plot gets thornier when you consider alternative explanations. Could these pits be sinkholes formed when underground lava tubes collapsed? It's possible, but most lava tube collapses leave rubble or tapered edges, while Mercury's pits are crisp and debris-free. Or perhaps they're the work of solar wind, which over eons could have eroded volatile-rich minerals into Swiss cheese. Yet solar weathering tends to create smoother, more uniform features, nothing as jagged or clustered as the pitted terrain. The most compelling clue might lie in the pit's relationship to Mercury's hollows. Both features share a peculiar freshness, as if they're actively forming, and both defy the planet's otherwise ancient, battered surface. Are they different stages of the same process? Could degassing pits evolve into hollows over time, or are they distinct phenomena with separate origins? Until we land a probe near one of these volcanic badlands to study them up close, the pitted terrain will remain one of Mercury's most tantalizing riddles, a landscape where fire met ice and the ground itself seemed to breathe. What's undeniable is that these pits are more than just scars. They're ghostly imprints of a time when Mercury was a world of fire and frenzy. Whether carved by explosive gases, crumbling lava, or something even stranger, they whisper secrets about the planet's volatile past and hint that beneath its quiet exterior, Mercury might still hold a few explosive surprises. Beneath Mercury's relentless sunlight lies a riddle wrapped in shadow, vast expanses of oddly dark terrain that absorb sunlight like cosmic black holes. These patches, dubbed low-reflectance material by scientists, are so profoundly dark that they stand out starkly against the planet's otherwise reflective surface. Unlike the sooty deposits you might find on the Moon or Mars, this material doesn't just dim the landscape, it devours light, reflecting less than 5% of the sunlight that hits it. What makes this phenomenon so baffling isn't just the darkness itself, but where it appears. These inky blotches sprawl across Mercury's most ancient geological formations, hugging crater floors and clinging to the edges of volcanic plains like stains from some primordial spill. One leading theory suggests we're looking at the last remnants of Mercury's original crust, a carbon-rich shell that formed when the planet was young. Picture this: 4.5 billion years ago, as Mercury's magma ocean cooled, graphite, a form of pure carbon, might have crystallized and floated to the surface like scum on a pond. Over time, volcanic eruptions and asteroid impacts could have buried most of this graphite layer, leaving only these scattered, shadowy scraps behind. It's a compelling idea, especially since lab experiments show graphite reflects light almost as poorly as Mercury's dark patches do. But here's the wrinkle: if this material is really ancient carbon, why hasn't it been baked away by the sun's relentless radiation? Graphite isn't invincible. Over billions of years, solar winds and micrometeorites should have eroded or darkened it further, yet these patches remain pristine, as if time forgot them. Then there's the volcanic angle. Some researchers argue the darkness might come from titanium-rich minerals like ilmenite, which volcanoes could have spewed across the surface in Mercury's fiery past. On the Moon, ilmenite creates dark splotches in lunar mare, but Mercury's patches are darker and more concentrated, almost as if something amplified their light-absorbing properties. Others propose an even wilder idea, that the material isn't native to Mercury at all. Comets and carbon-rich asteroids could have bombarded the planet, leaving behind layers of organic compounds that, under the sun's harsh glare, polymerized into a tar-like substance. Imagine interstellar soot slowly accumulating over eons until it formed these vast shadowlands. The mystery deepens when you examine the patch's distribution. They're not random, they cluster near Mercury's most heavily cratered regions, as if tied to the planet's oldest wounds. Some even overlap with the planet's mysterious hollows, those bright, shallow depressions that seem to actively reshape the surface. Could the two features be connected? If the dark material is rich in volatiles, its gradual disappearance might explain why hollows form nearby, like watching a cosmic ice cube sublimate and leave behind a gaping hole. But that raises another question. Why don't we see similar dark patches elsewhere in the solar system? Mars has its dark dunes, and the Moon its titanium-stained plains, but nothing matches Mercury's eerie, light-swallowing stains. The most tantalizing clue might come from Mercury's poles. Some low-reflectance material lurks near permanently shadowed craters where water ice survives, sparking speculation that the darkness could be a mix of carbon and frozen organics, a sort of primordial sludge preserved in the cold. If true, it would mean Mercury isn't just a scorched wasteland. It's a museum of the solar system's original building blocks, a place where the ingredients for life might have been stored untouched for billions of years. For now, though, these shadowy patches remain one of Mercury's most stubborn puzzles. Whether they're relics of a lost graphite crust, volcanic oddities, or something even stranger, they force us to reconsider how planets form and evolve. Every probe sent to Mercury peels back another layer of the mystery, but the truth remains just out of reach, hiding in the darkest corners of the solar system's smallest planet. And until we land a rover in those Inkai plains to scoop up a sample, we're left staring into the abyss, wondering what secrets it's still keeping. Mercury is missing something vital, a mantle. For a planet that's mostly core, the absence of a thick, rocky layer between its metallic heart and its crust isn't just unusual, it's planetary sacrilege. Earth's mantle makes up over 80% of its volume, a churning engine of heat and motion. Mars has one. Even the Moon has a mantle, albeit a thin one. But Mercury, its mantle is so scrawny, some scientists argue it might not even count. This isn't just a curiosity, it's a full-blown crisis in planetary formation theory, forcing us to ask, was Mercury's mantle stolen, vaporized, or was it never there to begin with? One explanation drops us straight into the chaos of the early solar system, a time when planets were still brawling for space. Imagine a young Mercury, freshly formed with a respectable mantle, only to suffer a catastrophic collision with a protoplanet the size of Mars. The impact wouldn't just shake things up, it could have blasted away most of Mercury's outer layers, leaving behind a skeletal core dressed in a threadbare mantle. Think of it like a cosmic peach pit, the juicy fruit stripped away by violence. Computer simulations support this idea, showing that high-speed impacts could shear off a planet's mantle while leaving its dense core intact. But here's the snag. If Mercury lost so much material, where did it go? Some models suggest the debris could have spiraled into the Sun, while others propose it was scattered so widely that even telescopes can't spot the traces. Then there's the radical alternative. Maybe Mercury never had much of a mantle to begin with. Instead of forming from the same swirling dust cloud as its planetary siblings, Mercury might have been born in a pocket of the solar nebula, unusually rich in metals and poor in silicates. Picture a construction site where the delivery trucks only brought iron beams, leaving the bricks behind. If true, this would mean Mercury was always destined to be a metal-dominated oddball, its composition preordained by the chemical quirks of its birthplace. Supporting this, Mercury's surface is curiously low in aluminum and calcium, key ingredients in a typical rocky mantle, suggesting those elements were scarce from the start. But the plot thickens when you consider Mercury's volcanic past. The planet's vast smooth plains are ancient lava flows, proof that some mantle material once existed to melt and erupt. If Mercury's mantle was always thin, how did it produce enough magma to resurface entire regions? One possibility is that its mantle wasn't just thin, it was weird, packed with sulfur or other volatile elements that lowered its melting point, allowing even a meager layer to produce outpourings of lava. It's like comparing gasoline to wet logs. One burns explosively even in small amounts. The implications ripple far beyond Mercury. If giant impacts can strip a planet to its core, that might explain similar metal-rich worlds spotted orbiting distant stars. If mantles can be optional, it forces us to rewrite the recipe for how rocky planets form. Even Earth's history comes into question. Did our planet narrowly avoid a mantle-stripping catastrophe, or was it just luckier in its choice of building materials? For now, Mercury's missing mantle remains a gaping hole in our understanding, a silent reminder that the solar system's birth was messier and more violent than we ever imagined. Every new mission, every fresh simulation, brings us closer to the truth, but until we can drill into Mercury's crust or catch a mantle thief in the act elsewhere in the galaxy, this conundrum will keep planetary scientists awake at night, staring at the sky and wondering, where did it all go? The Caloris Basin isn't just Mercury's biggest scar. It's a gravitational rebel, bending the rules of physics in ways that leave scientists staring at their data in disbelief. Stretching over 900 miles wide, this colossal impact crater should be a textbook example of planetary trauma, a giant hole punched into the crust surrounded by fractured terrain. But when NASA, a messenger spacecraft, mapped the basin's gravity field, it uncovered something far stranger. Instead of the expected dip, a gravitational slump from missing mass Caloris boasts a stronger pull than its surroundings, as if something hidden beneath the surface is tugging at the planet with invisible hands. So what's lurking under this ancient wound? One leading theory points to a subterranean ocean not of water but of magma. When the asteroid or comet that carved Caloris struck Mercury billions of years ago, the impact might have been so violent it melted the mantle below, creating a temporary sea of molten rock. As that magma cooled, dense minerals like iron and titanium could have sunk, forming a thick, metal-rich layer that now warps gravity like a buried anvil. Supporting this, Caloris sits atop one of Mercury's oldest volcanic provinces, where lava once flooded the landscape. If the impact reignited that fire, the aftermath could have left behind a dense, frozen sludge planetary scar tissue with an unnaturally heavy grip. But here's where the plot thickens. Alternative models suggest the anomaly might not be homegrown at all. It could be a cosmic hitchhiker. The object that smashed into Mercury might have been unusually rich in heavy metals, leaving behind chunks of its own core embedded in the basin floor. Imagine a bullet fired into a block of wood, but instead of shattering, the bullet's metal core stayed intact, lodged deep beneath the surface. That would explain the gravity spike without requiring Mercury's interior to behave in unconventional ways. Yet even this explanation feels shaky. Most impactors vaporize on collision, scattering their material too thinly to create such a concentrated mass. For this to hold, the Caloris impactor would have needed to strike at just the right angle and speed to bury its metallic heart without obliterating it, a cosmic hole in one with odds almost too slim to calculate. The wildest possibility, Mercury's crust might be playing tricks on us. Some researchers propose that the impact shockwaves could have compressed the planet's already iron-rich mantle, squeezing it into a denser configuration that persists to this day. Think of it like crumpling a soda can. The metal doesn't disappear, it just gets packed tighter. If true, Caloris's gravity anomaly isn't an imported oddity or a magma relic. It's a permanent dent in Mercury's very structure, a gravitational echo of the impact's raw power. What makes this mystery so gripping is its implications. If the anomaly stems from condensed mantle, it challenges our understanding of how planetary interiors respond to trauma. If it's impactor debris, it suggests some cosmic collisions are far stranger than we imagined. And if it's frozen magma, it hints that Mercury's volcanic past was even more extreme than its scarred surface lets on. Every theory brushes against bigger questions about planetary formation, about the violence of the early solar system, about how worlds heal or don't after cataclysm. For now, Caloris keeps its secrets locked beneath a battered plane, a gravitational riddle wrapped in impact-blasted rock. Until we drill through those ancient lava flows or send seismic sensors to listen for echoes of that long-ago collision, this basin will remain one of Mercury's most tantalizing contradictions, a crater that weighs heavy on the mind even as it defies the scales. Mercury might be hosting an invisible dance right under our noses, elusive, gossamer thin rings of dust that shouldn't exist, yet stubbornly refuse to be dismissed. Unlike Saturn's icy, show-stopping halos or Jupiter's faint bands, these proposed dust rings would be so ethereal they'd make cobwebs look sturdy, clinging to space around the smallest planet in ways that defy every expectation. The idea sounds absurd at first glance. How could a world with no substantial atmosphere and a puny gravitational pull corral enough debris to form rings? But the whispers of their existence come from curious, hard-to-ignore observations, fleeting dips in sunlight, odd scattering patterns in telescopic data, and unexplained glints that hint at something orbiting Mercury unseen. The case for dust rings hinges on Mercury's brutal relationship with the Sun. Solar radiation and the planet's lack of atmosphere mean any loose particles should be blasted away or sucked into the star's gravity well almost immediately. Yet there's a tantalizing loophole. Lagrange points, gravitational sweet spots where Mercury's pull and the Sun's balance just enough to trap debris temporarily. Earth has clouds of dust in its own Lagrange points, why not Mercury? Some models suggest that micrometeorites chipped off Mercury's surface by impacts could get snagged in these zones, creating wispy, ever-shifting rings too faint to see directly. The dust wouldn't stick around forever, maybe a few weeks or months, but constantly replenished by new impacts. These phantom rings might flicker in and out of existence like a celestial mirage. The real bombshell, we might have already glimpsed them. In the late 1990s, astronomers using solar telescopes noted strange, asymmetrical brightening around Mercury's orbit, flares of light that didn't match known comet trails or zodiacal dust. Decades later, NASA stereo spacecraft spotted similar anomalies, faint, ribbon-like structures near Mercury's orbit that defied easy explanation. Could these be the shadows of dust rings backlit by the Sun? Skeptics argue the observations might just be instrument artifacts or scattered light, but proponents counter that the patterns align eerily well with where Mercury's Lagrange points should collect debris. And then there's the wild card, Mercury's magnetosphere. Unlike Earth's orderly magnetic field, Mercury's is a tangled mess, with magnetic tornadoes funneling solar wind particles down to the surface. These chaotic forces could theoretically shepherd charged dust particles into unstable rings, like iron filings caught in a magnetic swirl. If true, Mercury's rings wouldn't just be passive debris, they'd be dynamic, shape-shifting structures molded by invisible forces, vanishing and reforming in hours. The implications would ripple far beyond one tiny planet. If Mercury, of all places, can harbor rings, it forces us to rethink how delicate structures persist in hostile environments. Maybe Venus hides similar veils of dust. Maybe exoplanets scorching close to their stars have ghostly rings we've never thought to look for. Until a dedicated mission like ISA's upcoming BP Colombo snaps definitive proof, though, these hypothetical rings remain the solar system's ultimate maybe, a tantalizing whisper at the edge of detection, reminding us that even the most unlikely places can harbor the most delicate wonders. Mercury's smooth plains stretch across the landscape like frozen oceans of rock, vast, eerily flat expanses where the usual chaos of craters and cliffs gives way to an unsettling serenity. These regions, some larger than entire countries on Earth, look almost polished under the sun's glare, their surfaces so unblemished that they seem out of place on a planet otherwise defined by violence. The mystery isn't just their smoothness, it's the fact that they exist at all. In a solar system where ancient surfaces are typically pockmarked with impact scars, Mercury's plains are like blank pages in a book otherwise filled with scribbles, and scientists are locked in a tug of war over what wrote them. The volcanic camp has the most straightforward explanation: lava. Imagine Mercury billions of years ago, its interior still seething with heat. Enormous eruptions could have flooded low-lying basins with molten rock, drowning older terrain under miles of basaltic flows. As the lava cooled, it would have solidified into those vast, flat plains we see today, much like the lunar Maria that darkened the moon's face. Supporting this, spacecraft images reveal wrinkled ridges, long, wave-like deformations snaking across the plains, features common in lava fields where molten rock contracts as it hardens. Some plains even show ghostly outlines of half-buried craters beneath them, as if the lava barely filled the basins before freezing. It's a tidy story, but here's the snag. Mercury's smooth plains aren't just flat, they're too flat, lacking the telltale cracks, vents, or volcanic domes you'd expect from a fiery past. That's where the impact theory kicks in. Picture an asteroid the size of a small moon slamming into Mercury with such force that it doesn't just carve a crater, it melts the surface for thousands of miles around. The energy from the collision could have liquefied the crust temporarily, creating a short-lived ocean of molten rock that, as it cooled, smoothed out like chocolate syrup on a frozen plate. This would explain why some plains radiate from known impact basins, their edges blending seamlessly into the surrounding chaos, even more compelling. The plain's composition matches Mercury's crust, not the deeper mantle material you'd expect from volcanic outpourings. It's as if the surface wasn't flooded from below but stirred from above, like a spoon swirling through hot soup. Yet neither theory fully solves the puzzle. If the plains are volcanic, why do some contain mineral signatures unlike typical lava? Spectrometers have detected odd concentrations of magnesium and sulfur, elements that usually stay buried deep in the mantle. And if impacts are to blame, why do some smooth plains lack any clear connection to known craters? The most baffling examples sit in isolation, their origins untethered to any obvious catastrophe. Then there's the wild card, a hybrid origin. Perhaps some plains began as impact melt, while others formed from volcanic eruptions triggered by those very impacts. Mercury's crust, already stressed by the planet's shrinking core, might have fractured like an eggshell under siege, allowing magma to seep through the cracks. In this scenario, the smooth plains aren't just one thing, they're a patchwork of disasters, each telling a different chapter of Mercury's fiery youth. The stakes here are higher than they seem. If the plains are volcanic, they could reveal how small planets release internal heat long after formation. If their impact melt, they might rewrite the rules of how collisions reshape worlds. And if they're both, that opens a Pandora's box of planetary evolution, where chaos and fire work in tandem to sculpt surfaces in ways we're only beginning to grasp. For now, these silent plains keep their secrets, their smooth faces hiding a past more turbulent than we ever imagined. One thing's certain, Mercury's serenity is a lie. Beneath that calm exterior lies a history written in fire and fury. Mercury's days and nights aren't just opposites, they're extremes locked in a cosmic tug of war, where temperatures swing so violently they could shatter ordinary matter. When the sun climbs overhead, the surface bakes at 800 degrees Fahrenheit, hot enough to liquefy lead. But as night falls, that same ground plunges to minus 290 degrees, colder than Pluto's shadowed valleys. That's a 1,200-degree roller coaster every single day. Yet even in this brutal cycle, Mercury harbors a thermal oddity. Some regions cling to their heat like a fading ember, cooling slower than physics says they should. These twilight zones defy the rules, hinting at secrets buried just beneath the planet's scorched skin. What makes these slow cooling patches so baffling? For starters, Mercury's lack of atmosphere should make heat vanish like a snuffed candle. On Earth, air molecules trap and redistribute warmth, smoothing out temperature swings. But Mercury's exosphere is thinner than a scientist's patience after a failed experiment. Particles are so sparse they might as well not exist. Without this thermal blanket, the surface should shed heat instantly when sunlight fades. Yet certain areas, particularly near crater rims and rugged terrain, linger in the twilight, radiating warmth long after their surroundings have frozen solid. It's as if the ground itself has a memory, stubbornly holding onto the day's furnace-like embrace. One clue lies in Mercury's soil. The topmost layer, or regolith, isn't uniform. Some patches are fluffier, packed with tiny gaps that act like insulation. Think of it like a thermos. The more porous the material, the slower heat escapes. Micrometeorite impacts over billions of years could have pulverized certain regions into a fine, airy powder while leaving others densely packed. But here's the twist. This alone doesn't explain the scale of the anomaly. The slow cooling zones aren't just slightly warmer, they're thermal rebels resisting the night's chill with almost supernatural tenacity. Then there's the subterranean angle. Some scientists suspect these regions might hide underground networks of cracks or hollows, microscopic caverns where trapped heat leaks back to the surface at a trickle. On Earth, lava tubes and fractured bedrock can store warmth for weeks, but Mercury's version would need to be far more efficient. If the planet's crust is riddled with narrow fissures, they could function like a planetary radiator system, slowly bleeding stored solar energy into the night. Supporting this, some slow cooling zones overlap with areas where MESSENGER detected possible hollows, those enigmatic, glittering pits that might be exhaling volatiles. Could escaping gases leave behind porous, heat-trapping labyrinths? The wild card, Mercury's minerals, certain compounds like sulfides or metal oxides, absorb and release heat at unusual rates. If the slow cooling zones are rich in these materials, they might act like thermal batteries, soaking up sunlight greedily by day and dispensing it reluctantly at night. It's even possible that solar wind, the relentless barrage of charged particles from the sun, has altered the surface chemistry over eons, creating patches that behave like cosmic rechargeable heaters. The stakes here reach beyond Mercury. If we can unravel why some patches defy the cold, it might rewrite how we design spacecraft to survive extreme environments. Imagine landers using naturally heat-retentive terrain as thermal shelters, or probes tapping into subsurface warmth to extend their lifespans. More profoundly, these twilight zones remind us that even airless, seemingly lifeless worlds have their own rhythms, hidden, intricate, and waiting to be decoded. Every temperature anomaly is a whisper from Mercury's depths, a clue that this scorched little planet still guards mysteries as layered as its tortured crust. After decades of staring at Mercury through telescopes and brief flybys, scientists thought they had a handle on its quirks, until BP Colombo started whispering back secrets no one expected. Launched in 2018, this European-Japanese mission is the most advanced probe ever sent to the solar system's innermost planet, armed with instruments so sensitive they could detect a snowflake falling in a hurricane. Yet instead of neatly answering old questions, BP Colombo is uncovering puzzles so perplexing they've left researchers scrambling to rewrite their models. Take Mercury's lopsided magnetic field, for instance. Earlier data from NASA, a messenger mission, suggested the field was weak and off-center, like a flickering flashlight with dying batteries. But BP Colombo's magnetometers have spotted bizarre, high-frequency fluctuations, rapid pulses of magnetic energy that dance across the planet's surface like invisible lightning. Some scientists suspect these could be signs of liquid metal sloshing unevenly in Mercury's core, creating chaotic currents that warp the magnetic field in real time. Others propose a wilder idea, that solar wind particles are ricocheting off the planet's surface, temporarily magnetizing patches of crust in fleeting, unpredictable bursts. If confirmed, this would make Mercury the only known world where the ground itself briefly becomes a magnet, a cosmic chameleon changing its stripes under the sun's glare. Then there's the exosphere, that wispy shroud of gas clinging to Mercury like a ghostly fingerprint. BP Colombo's spectral analyzers have detected sudden surges of sodium and oxygen atoms in regions where they shouldn't exist, far from the poles and in broad daylight, where solar radiation should vaporize them instantly. Even stranger, these atoms appear to be clumping together in microscopic clusters, defying the usual behavior of gases in near-vacuum conditions. Could Mercury's surface be exhaling these elements through hidden geysers? Or is some unknown chemical reaction bonding atoms together like cosmic Velcro? Every new data dump from the probe deepens the intrigue, revealing an exosphere that behaves less like a predictable gas layer and more like a living thing, breathing, pulsing, and refusing to follow the rules. The mission's biggest revelation, though, might be hiding beneath Mercury's scarred skin. BP Colombo's gravity sensors have mapped subtle density variations that suggest the planet's core isn't just partially molten, it's layered with concentric shells of metal alloyed with lighter elements like silicon or sulfur. This discovery throws a wrench into every existing model of planetary formation. If Mercury's core cooled in stages, crystallizing from the inside out like a cosmic onion, it could explain why its magnetic field hasn't faded completely over billions of years. But here's the twist. The probe also detected unexpected seismic murmurs, tiny vibrations that might be mercury quakes rattling through the crust. Are these tremors caused by the core's gradual solidification, like ice cracking as it freezes? Or is Mercury's surface still adjusting to the slow-motion collapse of its shrinking interior? Perhaps the most tantalizing mystery BP Colombo could solve is the origin of Mercury's dark shadows, those pitch-black patches near its poles where even the sharpest cameras struggle to pierce the gloom. Early spectrometer readings hint at complex organic molecules mixed with the ice, compounds far more intricate than the simple carbon chains delivered by comets. Some researchers whisper about the possibility of prebiotic chemistry, a frozen laboratory where the building blocks of life might have been preserved for billions of years. It's a long shot, but if the probe finds evidence that Mercury hoarded these materials through its fiery history, it would force us to reconsider where and how life's ingredients can survive in the universe. With years of observation still ahead, BP Colombo is far from done unraveling Mercury's enigmas. Every orbit peels back another layer, revealing a world that's stranger, more dynamic, and more defiant of expectations than anyone dreamed. Whether it's decoding the core's cryptic heartbeat, catching the exosphere mid-transformation, or hunting for shadows where the universe's oldest recipes might still linger, one thing's clear: Mercury isn't just a relic of the solar system's past. It's a living puzzle, daring us to rethink what we know about planets, and BP Colombo is just starting to listen. most planets wear their age on their sleeves, cratered, battered, and frozen in time. But Mercury might be the solar system's master of disguise, hiding volcanic youth beneath its ancient face. Scattered across its sun-blasted plains are lava flows so smooth, so pristine, they look like they might have oozed onto the surface yesterday. These aren't the weathered scars of a long-dead world. They're fresh enough to make scientists question everything we thought we knew about when Mercury's fiery heart finally went cold. The controversy starts with a simple observation. Time leaves marks. On the Moon, ancient lava flows are pockmarked with countless impact craters, their surfaces dulled by billions of years of micrometeorite strikes. Mercury's supposed old flows, though, some look like they've barely weathered a single cosmic storm. High-resolution images from NASA, a messenger mission, reveal plains with shockingly few craters, fewer than even the youngest Luna Maria. One standout example lies near the planet's north pole, where a vast expanse of smooth terrain shows barely a scratch, as if the lava cooled just in time to dodge the solar system's last few eons of asteroid bombardment. But here's where the debate ignites. Conventional wisdom says Mercury's volcanic activity sputtered out around 3.5 billion years ago, not long after the planet formed. The energy required to keep magma flowing on such a small world, one that should have lost its internal heat to space eons ago, simply shouldn't exist. Yet spectral data complicates the story. Certain lava flows contain mineral signatures that degrade rapidly under solar radiation, suggesting they couldn't have been exposed for more than a few 100 million years. It's like finding a still steaming cup of coffee in a house abandoned decades ago. Something doesn't add up. One radical theory suggests Mercury's volcanism wasn't a one-time event but a slow-burning saga. Unlike Earth, where plate tectonics constantly recycle the crust, Mercury's stagnant outer shell might have acted like a pressure cooker, trapping heat beneath the surface until episodic bursts of magma punched through. Imagine a pot boiling over intermittently, each eruption small but collectively spanning far longer than models predict. Supporting this, some flows appear layered, with older lava overlaid by younger patches, hinting at multiple eruptions separated by vast stretches of time. The wild card, tidal heating. Mercury's eccentric orbit subjects it to extreme gravitational tugs from the Sun, which could have flexed its interior like a stress ball, generating just enough warmth to keep magma oozing into recent geologic history. Even today, as the planet's core slowly solidifies, the release of latent heat might fuel the occasional volcanic hiccup, enough to explain those eerily fresh-looking plains. For skeptics, though, the answer lies in optical illusions. Mercury's lack of atmosphere means erosion happens at a glacial pace. A lava flow exposed 1 billion years ago might retain its smoothness simply because there's no wind or rain to wear it down. Others argue that impact melt debris liquefied by asteroid strikes could mimic young volcanic features without requiring deep-seated magma. The implications are planetary scale. If Mercury stayed volcanically active for even a fraction longer than assumed, it reshapes our understanding of how small, rocky worlds evolve and where we might hunt for signs of recent eruptions on exoplanets. Every new image from BP Colombo's ongoing mission inches us closer to the truth, but for now, these suspiciously youthful flows remain one of Mercury's most tantalizing contradictions, a world that refuses to fade quietly into geologic retirement. From its bizarre magnetic field to its inexplicable hollows, from the ghostly glow of blue halo craters to the eerie warmth hiding in its polar shadows, Mercury isn't just a planet, it's a cosmic rebel, defying every expectation we've ever had about small, rocky worlds. We've counted down 25 of its most jaw-dropping mysteries, each one peeling back another layer of this tiny enigma. Mercury shouldn't have ice, yet its poles hide frozen water. It shouldn't have a magnetic field, yet it flickers unpredictably like a dying light bulb. Its surface should be iron-rich, yet vast stretches are mysteriously metal-poor. And let's not forget those haunting hollows, glistening pits that seem to rewrite themselves in real time, defying every rule of planetary geology. But why does any of this matter? Because Mercury isn't just a curiosity, it's a time capsule, preserving clues about the solar system's most violent, chaotic era. Every anomaly, every contradiction forces us to rethink how planets form and evolve. Its oversized core challenges our models of planetary collisions. Its volatile, rich surface hints at a birthplace far from the sun's scorching grip. Even its wispy exosphere and phantom-like tail teach us how airless worlds interact with the relentless stellar winds battering them. If we can unravel Mercury's secrets, we're not just understanding one world, we're decoding the hidden rules that shape all rocky planets, from those in our cosmic backyard to the thousands we've spotted orbiting distant stars. So now it's your turn. Which of Mercury's mysteries captivates you the most? The way it shrinks like a raisin in the cosmic oven, the dark stains that swallow sunlight whole, or the X-ray auroras that flicker like a dying star's last gasp? Drop your thoughts in the comments. We'd love to hear which puzzle keeps you up at night. And if you're hungry for more deep dives into the universe's strangest corners, don't forget to subscribe and hit that notification bell. The cosmos is full of enigmas, and we're just getting started. Until next time, keep looking up, because out there, even the smallest worlds hold the biggest surprises.